Hi. Right, so we're going to be addressing number systems. We're going to be dealing with various kinds of number systems. And we're first of all going to deal with real number systems. Right, so how do we build this up? How did number systems become part of us all? A little bit of a story to numbers. It's a lovely story to tell, right? And we will deal with real numbers in this tutorial. And we certainly won't deal with imaginary numbers for now. We're going to have another series on imaginary numbers sometime later when we're dealing with real topics, right, in the starting mathematical subjects of high school, right? So numbers, first of all, back in probably the caveman days somewhere, you can imagine someone who's never counted before, and all of a sudden he's got more than 3 or 4 things, and he needs to know how many there are, and he invented the words. Right, we don't understand that language anymore, but he invented the words and he started counting things and he gave names to those numbers. And these are called natural numbers or counting numbers. And one doesn't start counting at 0. We're all used to starting to count at 1, 2, 3, right? And those are the natural numbers. They start at 1 and you can count for as many items as what you've got words for. Right, whole numbers then came along, right? We have some of the ancient societies, specifically the Incas and the Egyptians, to thank for the discovery of the number 0. And hey, listen to me carefully, guys. 0 is a number. It's not nothing. There's a vast difference between nothing and a 0. 0 is a number. Nothing is exactly that. It's nothing, right? So we don't talk about 0 or O in mathematics. We talk about 0 in mathematics. We don't talk about O or nothing. Right, so whole numbers were 0 included, 0, 1, 2, 3, and so whole numbers incorporated all the natural numbers, but it added a 0 to the front of it. Then at some stage, people cottoned on to the fact that, hey, you can be negative in numbers as well. It's mostly when we started trading things where you would owe somebody money, or you would owe somebody sheep or goats or whatever, and your net worth would then be negative, so you'd owe the person -1 or -2 sheep or whatever the story was. And we then said, right, people started classifying all of those numbers as integers, and we classify it as integers today. So it starts at -infinity and it goes to +infinity from the left and to the right. This is just a convention, right? The concepts are what's important over here. So integers are -3, -2, -1, 0. And from there on, it's whole numbers. So integers incorporated whole numbers, and whole numbers incorporated natural or counting numbers. Right. But then there was a problem, because there's nothing in between. We don't know how to account for something in between 1 or 2, or 1 and a half, or between 0 and 1 as half, or a third, or minus a half, which is somewhere between 0 and 1. Somewhere over there in the middle is half, minus a half, and somewhere between that 0 and that 1 is plus a half. So rational numbers simply mean that there's a relationship, there's a ratio between the upper part, the 1, and the 2. So a rational number is a number that can be represented as A divided by B, or A ratioed to B, and where A and B are both integers. In any case, we'll have more on that just now. Then mathematicians started playing with numbers at some stage in the past. These are ancient mathematicians, and they discovered a whole bunch of numbers that were irrational. They're real, but they're irrational, right? So they have relationships, but those relationships cannot be pinned down, and we'll see more about that now. Okay, so let's have another way of looking at this, because we need to have a common way of representing numbers, and that's what's really, really important here, is we need to find a common way to represent numbers. So let's say we put all the natural numbers, right? These are all real numbers, the natural numbers, the counting numbers, real numbers, counting numbers, natural numbers. Let's call them natural numbers, the way we count, and we put them down, and we say, right, they are discrete values of 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. We know there can be as many of them as what there are. There's no 0, right? So if we add the 0, then the natural numbers become whole numbers, And now the whole numbers start at 0, and they go 0, 1, 2, 3, etc. But we retain knowledge of, in the reds here, for those are the counting numbers or the natural numbers. Right. If we add integers onto the line, we try and put them all on the same line. But now integers, I've got all the negatives. Right. So integers incorporated the natural numbers, and the natural numbers incorporated the counting numbers. So integers minus 6, minus 5, 4, 3, minus 1, 0, 1, 2, 3, 4, 5, but they were still discrete. So they were just points, right? They were represented just by points in the line in terms of where they're going. Right. So if we take this a step further, we say, right, how do we get these integers along a line properly? So we'd like to see them on a line because that's a way that we represent it. And it's just a convention that we start from the left with the negative numbers and we go to the right with the positive numbers. Right? And at the moment, integers, they're all discrete values. But if we put them on a line, then we can start determining the values between minus 1 and 0, for instance, or between 3 and 4, or between minus 6 and 5. And we know that they carry on forever to the left, so they get infinitely small in terms of negativity, and they get infinitely large in terms of positivity. We call these rational numbers. And rational numbers are very interesting because they can be written in the form of a upon b, where a is an integer and b is an integer. So let's have examples. 1 quarter, right? So the rational number, or the ratio, look at this word, ratio. The ratio of a to b is 1 to 4 is a quarter, and that's here somewhere, right? But it's actually a little bit more complex than that, because a rational number must be able to be determined exactly. So the ratio is 1 to 4, that's why it's rational, right? Or 0.25 in the decimal system can be determined exactly, and it lies there somewhere. It lies there somewhere, just between 0 and 1, a quarter of the way between 0 and 1, 0.25, and it's exactly determined, so it's a very good rational number. 29 upon 4 is also a rational number. It's a ratio, 29 to 4, 4 goes into 29, 7 and a quarter times, or 7.25. And we can exactly see where 7.25 lies. We can pin it down exactly on the line, right? And we're not concerned about it anymore. We know exactly where it is, right? Irrational numbers are an interesting anomaly to this, because most of them can still be written, or they can all be written as a upon b, but we can't find them exactly, right? Now, there's a very famous one. Right, one that we deal with, and there's a lot of work being done on this, and a lot of people study it. It's called pi, and pi is a relationship that pertains to circles, and we'll certainly see that when we do our introductory topics on circles. And pi is 22 upon 7. So the ratio, the rational part of it, is 22 divided by 7. But it's not a rational number, because guess what? Although it can be written as a upon b, right, it doesn't have a finite answer. We can never determine it exactly. There's no repetitiveness in it. We cannot find a finite answer. Now, if you take out your calculator and you take 27 and you do, 22, and you divide it by 27 in the same way as AB to that ratio, you'll find something like this on your calculator. That was from my calculator. It didn't want to do any further calculations on that for a very good reason, because it actually doesn't know how far it can go. So irrational numbers are real numbers, right? They can be written as a upon b, but we cannot pin them down. We cannot say exactly where it is. So we know it's 3.1415, etc. And it's a very, very interesting number. And just for a matter of interest, I've put about 250 or something like that decimals down for pi. There are computers in the world that are trying to calculate pi still, right? Well, they might have given up by now, I don't know. But back when I was a youngster, they were certainly trying to find out if there was a finite value of pi. And I know that they've now gone to billions of decimals of pi, but they cannot actually pin it down. That's very, very interesting. So pi is 3.1415, etc. But it carries on just about forever, right? And well, it does carry on forever, and there are websites out there that will display the first million decimals of pi for you. And I know that it's over billions already that they've calculated to try and find pi. And that's it. That's the real number system. Short and sweet. Have a look at the video again, right? Understand the concepts. These are real numbers. These are not imaginary numbers. Thank you very much.